Good morning, everybody, ladies and gentlemen. We have given some extra time for more colleagues to connect, and now it's time to start. Welcome again to the solar photovoltaic sessions. Today we are going to have a look at the project concept, definition, and project design. We're going to be running for a couple of hours, more or less, and eventually we will do a break in between. Okay, so let's move on. Okay, Bart introduced last week what would be the typical stages on an energy project. Okay, he was telling us about a reference list of about 8 steps, if you remember, from site assessment, energy demand assessment, resource, concept selection, etc. Okay, when we talk about photovoltaics, we also want to add a bit of a preliminary step, which would be what is the planning framework on an integrated approach. In fact, this is not only for photovoltaic, it's for all types of energy projects, but especially for photovoltaic, we will now discuss what do I mean with that. And in today's session we are going to cover the up to the 5th step, site assessment, the demand assessment, energy demand assessment, the solar radiation assessment, the different configurations, or the project concepts that we can envisage, and then the precising of the system and modeling. Okay, these are the steps that we're going to discuss today. Here, the last 3 points: the definition of outputs and inputs, the equipment and component requirements, and the operation and maintenance requirements, human resources. These are very much project specifics. Okay.
Eso perturba. Perturba. No.
Hello. Oh, okay. These are very much specific to the kind of project we talk about. Okay. So these last 3 points, they need to be specifically adapted to the kind of project we talk about. Next session will be about PV farms. So we will discuss the large PV plants. We will discuss these 3 points for the case of the large plants. Then when we resume the course in January, we will discuss about mini grids, off-grid mini grids, and we will see case studies, and a design exercise with these last 3 points for mini grids. And then also in January, we will analyze in detail the case of the rooftop, of the grid-connected small to medium PV systems. So these last 3 points, outputs, inputs, equipment, components, O&M requirements, etc., are very much project specifics. Okay. This is why today we will not cover them, but we will see them in the session really, devoted to each type of project. Okay, let's have a look at the first point, the strategic planning. Let me put a little bit of vision here, a little bit of philosophy, if you want. We are in a context of sustainable development, right? If we can go back some years in time when these visions were first formulated, 20 years ago, we had a vision of sustainability, which was the symbiosis or the connection of 3 main vectors: the social vector, the economic, and environmental. That was the convergence of the 3 key elements of sustainability. Of course, now we have some evolutions of these concepts from a specific energy supply point of view. This is an example I like from a company in the UK, which is called E4Tech, that they specifically adapt this concept, for the framework of energy services provision. And then we have some other vectors of analysis here: the policy, the business, and the technology. Okay, so we have a little bit of refinement of these concepts. After 14-15 years, this was evolved into some more detailed aspects of analysis. In any case, the bottom line here is that energy systems, and specifically PV systems, have to be, for them to be successful and sustainable, they have to be projects, complete projects, and not only installations, okay? Not only technical installations, infrastructure working. It is one first conclusion. And another one is the long-term vision. Planning for a long-term service is paramount, is of very utmost importance, meaning that issues like the management, the operation, the maintenance of our systems need to be carefully planned for. And if that is not going to be possible, or that is not going to be well deployed, that could be a reason enough to stop a project, or to decline the feasibility of a project. So, in an integrated vision of projects, we should, when we start considering a project, we should do a bit of a reflection. Yes, we should reflect a little bit, give some thinking. What do we mean by an integrated PV system? And here I have put a picture of a building here in Barcelona. This is the headquarters of the Institution of Architects in the College of Architects in Barcelona. And perhaps you cannot see, but in this facade and this facade here, we have PV systems, okay? There's glass and PV systems integrated in a vertical facade. Okay, so this is an option of integrating. Then we have another very different project, yes, a solar PV container solution for a community in Niger, in the West Africa. Again, we have PV system, but in this case, coming with a we could say plug and play solution, all right, in a container. Is this also an integrated project? Is this integrated PV system? I leave this question open for us to think. I think the answer is that, well, it depends, right? It depends. One thing is the physical integration, the organizational integration, etc. Yes, these two systems could be well integrated. It really depends. One thing is how to integrate the PV system into existing grids, if it is a grid connected system, which will lead us to some thinking about the land use, the land we are going to use, the available surface, etc. That has to be one aspect of integration. Then obviously PV systems need some support, some physical support. We can use existing buildings for that, like the example I just showed you in Barcelona, but also new buildings could be built as part of the PV system project. That's a possibility. If PV systems are going to be installed in buildings, obviously they need to be well integrated into the operations, the operational procedures of that particular building. Meaning that we need to check about the responsibilities, about maintenance, operation, monitoring, etc. Also, a very necessary reflection is what is the use of that building? What is going to be the use of this PV system, apart from generating electricity? Is this going to bring any other social use, like, I don't know, some kind of security issues in a rural community? Is that going to bring some socio-economic development because we need to create a cooperative to manage the PV system locally? Is this going to be a PV system in a hospital, in a school, where we are going to use that system for some sensitization, some awareness raising, some educational purpose, etc. Yeah? And also the integration on the architectural part of the building, yeah, that has to be also thought about. Finally, apart from the buildings, yes, integration into mini grids, into a village, the economic side of a PV system, of a mini grid, etc. So we can see all these elements that define the integration of a PV system. So a reflection, in that sense, is always well placed and necessary. So when we look at an integrated approach in a PV system, I think this is also valid for other technologies, of course. We have different components. We have the social component, where we are trying to design projects in a way that they bring equity in the electricity service, so nobody is left behind, all right? This has, of course, links to the demand assessment. Then we have an institutional or an organizational component, okay, that is related to the empowerment of the different stakeholders, the different institutions that take part in a project. Then we also have a technology or technical component, obviously, and the goal here has to be the reliability. The technology has to work properly with issues of quality. We have standards, we have norms, etc. to follow. And finally, the financial or the economic component, where the viability is the goal we need to follow. Some lessons learned, okay, in an integrated approach. This is a study on mini grids or microgrids. When there is problems, when there are problems in some of these components, then all the problems connect together, yes? And then we enter what they call a vicious cycle. So this is, leading to failure of a project, yeah? When there is underpriced tariffs, then obviously the money that is collected is not enough. Then there is poor operation and maintenance, then the demand cannot grow, then customers eventually, they do an overuse of the system, etc. Finally, unreliability of the system, financial non-viability, and then there is a cease of the functioning of this microgrid. Yeah, many mini-grid projects and rural electrification standalone projects have failed, perhaps not because of technology in the beginning, but because of institutional or organizational mismanagement or lack of capacity or lack of training, etc. Yeah? Or because of a financial problem, whatever. In the end, everything revolves and spiralizes, and the electricity service has to be stopped or stops because it's no longer sustainable. On the contrary, when things are properly planned and executed in an integrated way, we can think of a virtuous cycle where everything works together, and the electricity service can continue on and on with the difficulties, but being worked on and properly planned. Okay, so let's recap now. In this list, I'm going to put together these two elements. The site assessment will also contain the solar radiation assessment, okay? Because for the PV systems, when we analyze the site conditions, obviously we also take into account the solar radiation aspects, okay? So we can put together point 1 and point 3, okay? So in terms of site assessment, one of the first elements we need to look at, obviously, is the solar radiation levels that we have. This is something we already saw in the when we did the solar introduction to the solar to the photovoltaic and the solar generation part of our course, if you remember. For the solar radiation, we have essentially two types of data sources. One would be to collect our own data, very site specific, of course, go to the site and install data collection elements. The advantages, of course, are that we will have higher accuracy. The data collected will be very much, you know, the solar radiation being actually received in that very precise point, okay? But that will depend on the sensors we use, of course, the quality of the solar radiation measurement equipment we use, and also the time resolution. We can define that to be even for hour per hour or even less than that, yeah? So we can have a very precise and accurate measurement of the solar radiation that is received on the site. On the contrary, the difficulties are that we need to install this system. We need to have it in place for several months, yeah, to be able to capture what happens, you know, if there are any seasonalities or any changes from month to month, etc. Also, we could have extreme weather conditions like the storm you had last night, for instance. This could damage our measurement system, etc. Yeah. So it's an installation that needs to be there in place for several months, and it will not be the first time that. Hello? Sorry? Okay, that's fine, I think. Yeah, it will not be the first case that some data collection sensors or equipment is you know, damaged, and halfway through the recording, the collection of data, there's some missing gaps because of the problems with monitoring of the meteorological station. Yeah. Another possibility is to use, you know, geospatial or satellite recorded or modeled data, like the ones we discussed a couple of weeks ago. Yeah, the maps that are available to us. Obviously, this is quick and easy. This is available, but the accuracy, obviously, and the time resolution is very much limited, yeah, typically to daily averages, and we don't have hourly profiles typically available in those databases. But yes, we have the possibility to check long-term data, which is also convenient, because in a year we could have some particularities, or at least on very specific sites, yeah, even though the solar resource tends to be quite more, let's say, stable than the hydro resource, for instance, or the biomass. Yeah, even though there are some trends depending on the cases. If you look at long time series of data, you can see differences from solar radiation of about 5–10% depending on the sites. Yeah, this could happen, so it's always good to check that point. In case we are thinking of a project, probably a PV plant, a large PV plant, a solar park, or a project in a site, in a building where, you know, the performance has to be very critically assessed because it's a very sensitive site, hospital, or somewhere where we need a lot of accuracy, then we could be inclined to take our own data, site-specific measurements. Okay, the typically used equipment for that are the pyronometers, yeah, to capture the solar radiation. we have essentially two types of equipment, the pyranometers and the pyroheliometers. Okay, the pyroheliometers basically measure the direct radiation, okay, at a normal incidence. This is a pyroheliometer. The direct radiation is captured. Pyranometers are mostly used because they measure not only the direct radiation but also the diffuse, okay, radiation. On a planar, on a coplanar surface, they capture all the radiation that is received in a hemispherical, the hemispherical top, like a half a sphere on top of a given surface. Okay, so in practical terms, pyranometers are mostly used in solar systems. Like in this picture, you can see a type of pyranometer called a thermopyle pyranometer, which is installed in a PV system, in a solar plant, and that is very much useful to check what is the amount of solar radiation falling on the solar panels, and to compare that with the actual production of those PV panels to detect whether there is some kind of problem or deviation or underperformance of those PV panels, okay? The other main type of pyranometers that are used are photoelectric. They have a PV cell that is calibrated, okay? And these kind of pyranometers are also very much found in PV systems, not only in solar parks, but also small PV systems. I would recommend to install a pyranometer, yeah, solar radiation sensor that can help us to control the levels of irradiance being received in the solar panels constantly. Yeah? And then we can monitor that. Remember when we had the session with our colleagues from Ferntech in Germany, yeah, engineer Joan Tarragó was explaining us about their universal monitoring platform. One of the issues they can monitor, of course, is the solar radiation levels. Okay? Remember, we want to measure what pyranometers will be measuring for us is the irradiance in watts per square meter. That is a power flux. That is a beam, the intensity, let's say, of the solar radiation. When we measure irradiance over a certain period of time, typically a day, that's when we can calculate the irradiation, which is, okay, the distribution curve of irradiance. For instance, in a graph like this, the area under the irradiance curve will be the irradiation, and that has units of energy. All right, the energy received in our solar panels. Remember what we explained last week or a couple of weeks ago about the nominal power capacity of PV modules, yeah, the watt peak definition, standard test conditions, etc. And also the concept of the sun peak hours. Remember all of that, because when we use solar atlases or satellite data or maps, typically we get data on irradiation or sun peak hours. Okay. For instance, this map from SolarGIS, we have seen it, yeah, several times in this course already, and this is just to refresh some of the satellite data databases that are available. And some of the first three of them are public. Meteonorm, PVSys, you have to have a license, yeah, for that. And for instance, the Global Solar Atlas is very useful. We will get data on solar resource. But again, if we are going to install, or we are thinking about a project where we need a lot of precision, yeah, in the output estimation of our plant, perhaps the data in this kind of sources is not accurate enough for what we need. Then we might decide to install our own pyranometers in the field before deciding whether a project can go ahead or not. Okay, The next point that in a project we need to look at, of course, is the energy, the demand assessment. Okay, this is very much important for off-grid projects, obviously, but also for what we call the self-consumption grid-connected projects. Okay, those PV systems that will be connected to the grid in our house or in a building. Okay, in an office building, but will be primarily feeding the own consumption in the building, and then the balance of the surplus will be fed into the grid. In any case, the electricity demand needs to be understood and analyzed. Those of you working in off-grid systems, like colleagues from FUNAE, you're very much familiar with this. Other colleagues, perhaps you haven't come across these issues very much in detail before, but I think it's worth discussing this a little bit. Let me mute here somebody. Okay, I think we have. Do we have a question, or somebody wants to mute?
Como entrou como rap, entrou como isso aqui.
I think we can continue. He's struggling with the.
Okay.
Paul, we can continue. He's just struggling with changing the name. As you can see, it's Repe, not with his name. So.
Okay.
I tried to mute him. I hope I managed. And now we'll see. We can proceed, Paul.
Okay.
It's Henry. It is Henry.
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 Ah,
Henry
okay.
Matene. Henry Matene.
Yeah. Okay. So can you change there instead of having the Repe?
I want to change, but
if you go to, you just take. Okay. I will chat to you. I will write to you, so that we are not interrupting the class. I will chat to you directly. I will tell you how to do it. Yeah. Okay. You can proceed, Paul.
All right. Okay. So I was saying that for the electricity demand assessment, we need to remember that there are different levels of demand consumption. Yeah. This is a reference from the World Bank, from the Energy Service Management Access Program. The SMAP, where they defined 5 or 6 actually different tiers. Tier 0 would be no access. So 5 levels of electricity consumption, from very low loads, or very low consumption, low, medium, high, very high. Yeah, different tiers. Okay, depending on the kind of appliances that are considered or that are used in each tier. Okay. This is a study that I worked with the World Bank with the TTA, a company I work for, and you can see that this is a sample of different photovoltaic mini grids, okay, in Africa and Asia, and you can see that in each mini grid you can have a very different distribution, okay, of customers consuming in each of the different tiers. Okay, for instance, in this last one, a mini grid in Bangladesh with 360 connections, you can see that everybody was in the higher tiers, yeah, residential high or even productive. So every customer here was consuming quite a lot. Whereas, you know, a mini grid in Tanzania or a mini grid in Nigeria here, this one in Tungajika is a mini grid that was financed partially by GIZ, for instance. We can see that most of the customers were in tier number 2, the residential medium, yeah, like 85%, and the remaining 15% were either very small consumers or residential high consumers. Okay, so every mini grid has its own pattern of tier distribution. What is it I want to say here? is that you cannot take for granted, you cannot assume a specific pattern for electricity consumption. This is something that needs to be investigated on a project by project, case by case basis, because one village could be different to the next one, even if they are in the same province or in the same municipality. There is variability here. In any case, the demand is very critical, needs to be carefully assessed for off-grid PV systems, obviously, but also for the PV rooftop. It's for the self-consumption is interesting because we have a risk of either oversizing the system or undersizing it, where we will have inefficient performances, we will have unbalanced design of our system, we will have low quality of service if it is undersized, of course, with interruptions, with shortages of supply. And if we oversize it, well, we will have an increased budget, we will be, overspending, very large batteries, for instance, larger than what is strictly needed, or unexpected usage of backup genset if we have undersized it. We realize that we need more electricity, then we need to turn on the generators and consume fuel, which is very expensive. So if we don't understand the demand, if we don't analyze it properly, we have serious risks of having technical, service and financial problems. What we do normally is that we carry out some demand projection exercises, and basically for that we need to devise several hypotheses, different scenarios. We want to investigate a little bit what the sustainability possibilities of the system, meaning that in that community or in that village, do we have what kind of capacity to pay, what kind of willingness to pay will the users have, so that we can then adjust the demand together with the financial modeling of that project. The demand in the end is something that needs to be discussed together with the financial scheme that will be put in place to maintain the service. Also, what could be the present demand and what could be the future, the evolution of the demand. Typically in rural villages, when the light is there available, thanks to a mini grid or solar system, hydro, there will be changes. Not perhaps in the first day, but after some months or some years, some commercial activities will flourish, some more people will go and live in that community because there is electricity, etc. So we can anticipate that there will be some kind of growth, typically, or let's say some changes, some variability. Obviously, we need to anticipate that when we design the project. So balancing these two principles is fundamental, the economic sustainability and the evolution of demand in future scenarios. What types of loads do we have? Well, lighting, communications, motor-based applications, even heat generation applications, cookers, hair dryers, welding machines, whatever. Some kind of dryers for agro-processing could be electrical. Not so typical in this latitude for Mozambique, but why not? Each kind of load will have its implications, and the system design, lighting or communications could also be supplied with DC systems. No need for inverters then. When we think of motor-based applications, obviously in AC, then we can think of single-phase systems versus three-phase systems. If we need to cover a bit of a large area, we need a little bit of a low voltage distribution mini grid in a village, for instance. We might have advantages using it in designing it in 3-phase rather than single phase. What about the starting up power peaks of pumps, of engines? You know, we have very high peak currents at the startup, which could only last for not even seconds, milliseconds, but a very important peak that the inverter will have to be able to cope with that peak, to be able to supply that load, etc. Yeah. So the types of loads need to be understood and anticipated. Some references that I can give you are typically when we refer to basic consumptions, we are in the range of up to 20 kilowatt hour per month and below 500 watts, okay, of power demand. For the medium domestic category, we can have up to 50 kilowatt hour per month and 1000 watts demand, community demands, which could be school, health, center, public lighting, etc. And then productive uses that could be vary depending on the economic activities of the community, okay? And that will be above the previous values. These are just references you can keep. In the end, what is more important is to observe what we call the demand profiles, the load profiles, yeah? These kind of curves where we can see, we can observe what would be the power consumption levels during a day, yeah? During the hours of a day. This is the typical curve, I mean an example, where we can observe what the peak loads, the peak of these curves would be, the higher level of power consumption. And we can also typically observe a base load, yeah? A kind of load, a power consumption level that is kept, let's say, fixed, constant throughout the entire duration of the day. In here we can see this is the horizontal axis of time. We can see the hours in the day, from start of the day, midnight, 6 a.m., noon, 6 p.m., and midnight again. So understanding where the base loads are, the levels, yeah, the power consumption levels for base load, that would be typically the reference to design the battery system, for instance, all right? And then the peak loads are important to decide what kind of inverter, what kind of generator, even a backup would be possible, yeah, to cope with this peak of demand. Remember, we could have different load profiles for different days in the week. There could be a different weekly pattern, all right, for Sunday or for Saturday, for weekends, Friday, I don't know. And also we could have different patterns. Imagine the consumption in a school, right? Or a public building. We could have 1 month in a year or 2 months in a year when there is holidays, that the consumption is reduced. Yeah. Okay, so establishing the daily load profiles is important. Okay, to understand how to better design the PV system. There are some kind of loads that are particularly critical or necessary to understand. Apart from the base loads and the peak loads, what we call the manageable loads, the interruptible loads, those consumptions that we can stop if conditions of solar radiation or battery state of charge are not good. We can stop them and continue later on or the day after, like water pumps, like the utilization of freezers eventually, some loads that we can stop, or deferrable loads, those consumptions that we can move throughout the day. Typically, we want to move them during the time of the day where there's good solar irradiation, right? So when the PV panels will be generating nicely, then we can decide to use water pumps or washing machines eventually, or mixers to prepare some juice or some food or some machinery, etc. Okay, how do we investigate the electricity demand? We can use questionnaires, we can do surveys, interviews, etc. Okay. This means that we interact with the users, we do site visits, census, okay? For that, obviously, colleagues from FUNAI will have good experience, yeah, with that. This kind of exercises cannot be done quickly. You need patience, you need a lot of time to sit down with the users to discuss. The off-grid, the rural population, the families, the people who have not had electricity access before, they will not really know what is it, yes, about demand, what kind of demand levels. We cannot ask them about power, wattages, about appliances, because they will not know what to tell us, or they can tell us anything. So, yeah, each intervention has to be discussed probably with local stakeholders. We can have issues of the language as well. Yeah, we need to speak the local language of that community, of that province, etc. And typically, these kind of exercises are done in a training, yeah, with a training educational vision. All right. Anyway, so we have different challenges. The users are not experts. We need to assess not only the electricity demand they might have, the expectations they might have today, but what evolution they could have in the future. So we need to investigate if anybody in the community is planning to open a shop, a barber, a hairdresser, etc., 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 to see if that could be a substantial energy demand in the future. While we do these surveys and questionnaires, we can raise awareness, we can sensitize on energy efficiency, we can ask them what kind of fridges, what kind of appliances they're planning to use, and obviously always insist and advocate for, you know, low consumption devices like LED for the lighting, you know, low consumption fridges, etc. All right, there are different tools you can check. I'm sharing here a couple of links, yeah, from the MIT or even from the Energypedia. But yeah, in the end, what we need to do is to be able to fill in tables like this ones, where we have for each type, for each tier of consumption, this would be the very low, below the 20 kilowatt hour per month, yeah. We list the different appliances, we can find what would be the power demand for each unit, for each appliance, how many of them you can find in the household, how many hours of consumption it is expected. So that will bring us, that will give us the expected demand. This is very low. So in this example, this is from a project I did in West Africa, in Ghana. The very low consumption category was at about 10 kilowatt hour per month, all right? This would be the high end, the very high consumption or the high consumption, where each household was expected in that range, and this tier was expected to be consuming around 100 kilowatt hour per month. So you see the difference from 10 kilowatt hour per month to 100. And of course, here we can have the use of refrigerators, of iron, of color TV, fans, etc. And more lamps. Instead of 3 lamps, 8 lamps, because it's a bigger house, bigger compound, etc. Also investigate the commercial demand and the industrial demands, if anything at all. Yeah, in rural communities, there could be prospects for the flourishing of industrial activities. If we don't have time, or if we want to check the data we are getting from surveys and interviews, we can always compare the demand of a given community or a given site with the demand that is actually being registered in similar communities or similar village. Okay, so we need to understand what similar means. Similar socioeconomic, okay, patterns. If it is a fishing community, you know, along the river banks of the Zambezi River, for instance. So we can go to a community that is similar, similar demographics, etc., and that is connected to the grid, or that has already a mini grid, and we have data we can compare. And then we build a histogram, and then we adopt that pattern as a prediction, okay, for the community we are investigating. This is what I did in the project in Ghana, for instance. Got a message or something, no, that's fine. Hold on, I think there was some kind of message. Okay, well, let's continue. So this is the histogram of consumption, different meters in a community, in a similar village. And based on that, we prepared a histogram where we calculated what was the percentage of connections of customers under each category. Yeah, and this is what we found: 11% of 11% of the customers were in the very low segment, 33% in the low segment, meaning from 20 to 50 kilowatt hour, medium, high, or very high. And we can adopt these categories, which is in percentage, yes, to project the demand in the community we are studying. Yeah. And based on that, then we can build our load curves for the community we are investigating. Okay. In this case, we run a baseline scenario that would be the demand. This is a community in Ghana, Seneso community that had about 60 households, more or less. You can see in the daily load the different types of consumption we were projecting: residential, community loads, commercial, very, very little commercial activity, and some industrial activity, okay, small workshops. This was the baseline projection. But then we also built a couple of scenarios, yeah, considering demographic growth, population growth, but also increased productive activities, all right? Increased the appearance, the flourishing of shops, etc. in the community. This is why the demand curve, the load profile, you can see for the same community, after 10 years, we were projecting a growth in the demand that was actually 4 times the initial demand projection. Okay, you can see the peak growing. Remember the talk we had from our colleague from Studer, yeah? He mentioned the importance of understanding the demand, also to decide the kind of configuration, yeah, the power conditioning that we were going to adopt. Yeah? This is an example he shared with us, 2 types of mini grids. That the first type only with residential consumption, where we can see a typical residential load profile, yeah, with a higher consumption in the evening. And then another possibility, which is community with you know, higher community loads. We can see the public lighting, we can see some productive activities, telecom tower. Okay, we see the appearance of a base load that would be higher, yeah, and also a more higher consumption during daytime due to the productive activities. So the load profile substantially different. So depending on the level of irradiation, the level of solar resource received in that community, then the optimum coupling could be you know, a mixture of DC or AC. That depends on the kind of generation that we will have during daytime, or sorry, the matching of generation on consumption. Yeah, if we have 7 sun peak hours, then the optimum configuration would be 74% DC coupling, 26% AC coupling. And this share of AC and DC coupling could change depending on the level of irradiance. Same thing applies, the same thing happens when we have a village electrification model. Again, depending on the levels of radiation we find in the community and the load profile, well, the recommended coupling mix will be different, okay? So you see how important the load profile definition is in order to decide, yeah, how, in this case, the mini-grid coupling and the combination of DC and AC generation and power conditioning architecture, how these combinations could be optimized. It all depends on the demand profiles and the projections that are expected. So, to sum up, the demand assessment has a great influence in the off-grid PV system design. The load profile, it will influence the coupling, as we said, the configurations, the sizing of batteries, and also the modularity in the PV generation, the type of loads we will have, kind of power levels they have, if they are single or three-phase, etc. This will influence in the choice of our inverter and the modularity we can think of for the power conditioning. The evolution we can expect in the demand, yes, how certain we are, how sure we can be about the evolution of demand. Obviously, if we are very certain, we can come up with a very, you know, accurate design. If we are not very certain, we need to be flexible, yeah, and incorporate criteria of modularity, scalability, or even polygeneration, different generation possibilities, backup systems, to be able to cope with an eventual undersizing or limited capacity of the PV generation side of our plant, okay? And also, what happens if we are in an off-grid situation and the grid is arriving? Well, we need to consider in our design, you know, grid-compatible inverters and also protections, metering that will be able to work together with the grid. Okay. So let's move on to the next point. This would be very quickly, I'll go through the project concept selection and configurations. Obviously, when we address the design of a PV system, we need to be very clear about what kind of system we are approaching, all right? Whether it is an off-grid, whether it is grid connected, whether it is going to be hybrid, okay? We need to spend time define on that, whether it is a solar home system, simple project, whether it's going to be a residential system with AC consumption, meaning we need to incorporate the inverters. If we are talking about mini grids, what kind of mini grids, the autonomous or interconnected, all of these we have seen, yeah, in different sessions previously in this course. Let's remember about what we have learned in the previous sessions. If we have mini grids, we can always consider polygeneration, yeah, to adapt to changeability in the demand. Why not? Remember the example I mentioned about hybrid PV mini grid with wind in Ghana, or other possibilities, hybridization with hydroelectric generation, or with diesel genset backup, for instance. Remember also the session we had last week about different possibilities to interconnect mini grids with the grid, either distribution mini grids or centralized mini grids. Okay, so all these concepts, all these possible configurations we need to consider before we go for the pre-sizing. Yeah, we need some clarity on that. For the grid connection, grid connected applications, obviously we need to consider whether we will have a battery or not. Okay, and this will bring us to analysis of space availability, what would be the self-generation rate we expect, and in our configuration selection, at some point we will need to start doing cost analysis. How much our system is going to be costing, what kind of savings in grid consumption we can have, for instance, if it is a grid connected system, because the cost analysis might be a reason, if it's too high for our first design, we will need to revisit, yeah, and redefine the PV system design, make it simpler or change something, because our first design was too expensive. Yeah. For instance, another project that I did, in this case is for PV rooftops, the goal would be to try to optimize the matching between the load profile, which is the black curve, and the solar generation. Of course, this will depend on the kind of PV system that we consider. Yeah, the load profile is the same for a given building, all right, and the solar generation depends on the type of PV system that we consider. Sorry, this is a mistake. This is not 2000 kilowatt peak. This is 2000 watt peak. Okay, so it is double. So if we have double the size, we have double the amount of solar generation. Yeah, and obviously when the sun generates, if it is above the consumption levels we have, for instance, in a case like this, you can see that there is a lot of generation that will not be consumed in that same building during daytime. So unless we have the possibility to sell this electricity to the grid or to store it, this kind of situation will not be economic, will not be convenient, all right, in financial terms. You see, it can be possible technically, that's fine. We might have space in the roof to connect the 2 kilowatt peak or 2000 watt peak, but we will not be able to use all this electricity in the same building. So perhaps even if we have space in the roof, we are better off by downsizing the kind of PV system. For PV rooftop, what we consider are essentially two factors: the self-consumption, or the solar fraction factor, which is this curve here, and the self-consumption ratio, okay, which is this curve here. And these two curves, they change as we increase the size of a power system. This is for a given building, for a given demand situation in a building. When we start with a very small PV system, let's start with this curve. All the electricity generated by the PV system is consumed on site. So everything we generate with the PV system is consumed 100%. As we increase the PV system, we come to a moment where some part of the solar generation will not be consumed on site, which is when we are in these areas here or here. Yeah. As we continue increasing the PV system, the amount of electricity generated by this PV system that we can consume on site is lower and lower and lower. Okay. So there is a decrease on the solar fraction. Sorry, on the self-consumption ratio. Sorry, there is a decrease as we increase, as we make the PV system larger. For the solar fraction, well, as we increase the size of our solar generator, the amount of electricity that is covered by the PV system is higher, but we get to a maximum, you see? There is a point here where it doesn't really matter if we make our PV system larger, there is no way we can consume more electricity from it, okay? Because probably we have hit our maximum demand for that building. So there is an optimized size of a PV system that is technically defined by these two curves here, all right? Self-consumption ratio and the solar fraction. This has to do with PV rooftop. We will see this case in detail when we have our session about PV system rooftops in January. This is going to be, I think, towards the end of January. This is better to analyze it on a case by case, because this graph here corresponds to a particular building, and this will change from one building to another, okay? Okay, more configurations. Obviously, large plants are very different in their architecture to small PV systems. We have the protections, the kind of inverters are going to be very different. Then we have the connection to the substation, the transformer substation, and the connection to the grid. Obviously, this is very particular configuration for the large plants, and we will analyze this in detail next week when we discuss the case of solar farms, okay? Just to let you know, but according to the Spanish regulations, all this multiplicity of configurations has led to several types of regulations. You see, in Spain, for photovoltaic sistemas photovoltaicos, we have the autónomos, this is the off-grid, and the grid connected. So we have all. Sorry? Carlos?
No, it was Mr. Isufu Juma. He was not actually aiming to talk to us. I don't know why I don't know why he unmuted, and then we were hearing his conversation.
No problem, no problem. So I was just saying that, this configuration understanding and analysis and choice is important because we might have some particular regulation that applies to one configuration and not to a different configuration. In Spain, as an example, the legal framework we have now defines up to 8 different configurations, okay? Under administrative, economic, technical conditions are defined in up to 7 different regulations. So you have different instructions, technical instructions, different laws, different decrees, some of them have been published in different years, okay? So there is a regulatory side to this decision. In Spain, you need to understand what is it you are going to do, because you will need to follow one regulation or another. So in Mozambique, you have something similar, and you will have more in the future, with the new electricity law, and little by little with the self-generation and the net metering and the rooftop systems, you will have more regulations, I'm sure, in the near future. Okay, well, these are some nice configurations we can think. I hope Bart is here with us. Yes, Bart is here. In the future, hopefully for Mozambique, we can consider hybridization of solar photovoltaics and biomass. Why not? Some people call this agrivoltaics. Why not? This is a picture from Japan or Germany. One is from Japan, the other one is from Germany. So why not consider possibilities like this? More configurations we can consider, the smart grids, where we have a lot of interconnection with different potential consumers, and buildings that can generate with photovoltaics, schools, industries, hotel, hospital, you know, houses, households, housing blocks, whatever, and also charging, electromobility, yeah, charging stations for cars, and with a very developed grid network that can be sharing electricity, but also heat, cold, and of course a lot of data. Yeah, so this is a simple conceptualization of what we call a smart grid. Yes, and this hopefully for Mozambique we can be discussing this kind of approaches very soon. Yeah. Okay, so let's continue for another 50 minutes approximately. So before we move on to the pre-sizing and the modeling, I wanted to spend some minutes, yeah, mentioning about the institutional component. Of course, once we have an idea on the concept of the project, the configuration we would like, yeah, to assess, we need to know what kind of organizations, what kind of actors we will need for that project, and to check whether we have those actors in place. For instance, this is a very long list that I have, up to 17 different roles for a project, yeah? But all of these roles are important. Some of them are indispensable, yeah, indispensables. Some of them are recommended, okay? Who is going to coordinate this PV program if there are different projects? Who is the developer from the institutional point of view? There could be another developer from the social point of view. Projects can be developed from a top-down perspective or from a bottom-up perspective. Regulations, what regulations do we need to have in place for our project? Remember what I just mentioned. In Spain, for example, we have up to 8 different configurations, 7 different regulations to observe. And sometimes PV systems need to comply with multiple regulations, okay? Standards, what standards we need to follow. The funding, who is putting the money for our projects, who are going to be the users, okay, social developer. Sometimes in off-grid projects, the rural populations, we have somebody who is representing them. We have an NGO, we have a local cooperative, we have, I don't know, some kind of local platform that is developing the project for them, but it's only doing that, okay? It's an intermediary. We need technical direction, we need the engineering capacity, okay, construction capacity. We need an entity that's going to be generating the electricity. This could be different from the ones before. We need a service operator, could be the same as the generator entity or could be different, okay? Have different approaches, different power purchase agreements, etc. We need installers for the initial installation, construction of the plant, but we also need maintenance providers. We need technicians to do the maintenance, to go there every 3 months, 6 months, okay, every year. Optionally, if we have a hybrid system with biomass, with diesel genset, we will need a fuel supply, okay? And we need to have that also planned and prepared for. Okay, different providers of materials and equipment. Then let's not forget about training and communication in projects, okay, especially off-grid, very important. When you start with pilot demonstration projects, the communication part is very important. Then you need inspection, evaluation, and dissemination, probably. So you see, all these different roles need to be there. And sometimes, if we don't have a particular role there, a particular entity that has enough capacity to perform its obligation or its responsibility, that could be a reason, okay, not to go for that project. or to solve that before we go for that project. So this institutional capacity analysis is very important for all kind of projects. All right, so for precising and modeling, once our configuration is clear, or different configurations have been analyzed and have been discussed and prioritized, then we can think about the precising, okay? Even the precising can be done when we are comparing configurations, especially those configurations that could be quite close to each other, right? Like whether we do in a mini grid, we do a DC coupling or AC coupling or a mixture of both of them, okay? In a self-consumption PV rooftop project, whether we do a larger generation or lesser generation, or batteries or no batteries, okay? We can run the precising as part of the concept selection and configuration. So actually these 2 points, 4 and 5, can be interlinked, and 5 informs step 4 probably as well, yeah? So a generic list of steps we need to follow. As we said, we need to establish what the energy demand will be on a daily basis, critical for off-grid systems, very important for rooftops. And in the case of large PV plants, that's not something we need to do because the configuration is different now. We just generate as a power plant and to inject into the grid. The second step, as we have seen, the calculation of the radiation, yes, and taking into account seasonalities, taking into account the databases, etc. We have mentioned that. Then we need to calculate the PV power, photovoltaic generation power to be installed, watt peaks or kilowatt peak. Remember the sizing exercise, yeah, that we did for Gurue. Then we need to think about the mounting system, the structure, okay? This will also have to do with the site assessment, the conditions of the site. If we are talking about off-grid or in some self-consumption projects, the battery capacity, we will calculate. Then the power condition equipment, the regulator, the charge controller, inverters, protections, etc. Then this is not really about PV systems only. This is about an electrical, yeah, electrical system installation planning. We need, yeah, the conductors, the cabling, the sections, protections, etc. properly dimensioned. And in the case of grid-connected systems, then obviously we need to care about the interconnection and the interface with EDM, with the grid. Yeah. Essentially, we need to look at the main service panel protections and where to install it, etc. So this is a generic list of steps we need to, yeah, follow for the precising. So revisiting that again, solar radiation data. Remember PV sizing exercise that we did. Yes, remember about power performance ratio, the sun peak hours, this exercise that we did. Remember the performance ratio, yeah, the different values that we use. This would be, yeah, the formulas to determine the peak power capacity of a PV system given the energy demand or energy output that we want to achieve from that in PV system, okay? The performance ratio, the kind of losses we can have. And in here, I wanted to have a bit of a quick question to you. When we have this map, okay, this is a map we have been seeing very often, the global horizontal irradiation in Mozambique. And then we were also seeing this other map, yeah, which tells us the photovoltaic power potential, okay? This is in kilowatt hour per kilowatt peak, daily or yearly. And I wanted to ask you, okay, quick question. What is the change? What is the difference between this map and these two maps? Yeah, from this map here to this map here. What has changed? What is the difference? Who can tell me what happened between this map and this map? Very quickly, can we get some reactions, please? Dr. Lucas, I don't know if you might repeat the question in Portuguese, perhaps.
Well, yeah, I can repeat, but colegas, a pergunta é qual é a diferença entre esses dois mapas? Algum comentário? Qual é a diferença entre esses dois mapas?
Yes, the first, as we can see, in Maputo, from the first map, global horizon irradiation in Maputo is at all in the green. And as I can see, the results is very low. And in the second map, we can see it's a bit yellow. So
Okay.
it means that there are more radiation in the map on the right than the map on the left.
Any other idea? Somebody else? What do what do the rest think about our colleague opinion? He said there's less radiation here in this map than in here. Do you agree with this? Does anybody have a different opinion?
The left one is mentioned the irradiation. In the other one is mentioned the photovoltaic potential, the power potential. Is a different kind of maps.
Exactly.
They are not talking the same thing.
Correct. You're right. These two maps are different. Look at the units. This is irradiation, energy received per square meter. In the case of Maputo, somewhere around 4.9 kilowatt hour per square meter per day. And if we look at the yearly, would be 1,800 approximately kilowatt hour per square meter per year. Okay? This is irradiation. Now look at here. It's a different thing. Okay? It's not that the radiation in Maputo is different. It's not that this map is saying, you know, the radiation in, I don't know, in December and this is in June or the other way around, yeah? No. This is a different unit. This is the productivity, kilowatt hour per kilowatt peak. This is the power potential, okay? So there is a conversion here between this map and this map. These are sun peak hours and this is productivity. What is the conversion we have from this map to this map? Can somebody tell me? We have mentioned this in the class before, yeah? In the previous sessions, last week and 2 weeks before. Let me give you another tip. Somebody has estimated performance ratio here to change irradiation levels, solar irradiation levels to photovoltaic system productivity. Okay? Somebody has used the sun peak hours that this map is telling us to estimate the productivity of a PV panel, of a PV plant. And for that, we need the efficiency, performance ratio. How much is the efficiency considered in this map, which is using this other map as a source? What opinions do we have in the class? Please? You can use any point, yeah? If you like Maputo, concentrate on the data from Maputo.
What you said is you have to use the left map, horizontal irradiation.
Yes. Let's use Maputo as an example, okay? What is the level of irradiation we have on average per day? You can use 4.9, yeah? Approximately for the colors, 4.9. And look at the productivity, Maputo. It could be probably 4.3 kilowatt hour per kilowatt peak. Can you see there is a relationship? 4.3 over 4.9. How much is that in performance ratio? What efficiency of conversion is this? You understand?
Dê para perceber a pergunta, colegas?
Yeah, we're talking about this formula here. The map on the left is telling us the sun peak hours, and the map on the right is telling us the relationship between the power capacity and actually this one. We're talking about this formula here. Okay, this is the map on the right, and this is the map on the left. So the relationship between these two maps is the performance ratio. How much? If you take, for instance, the case of Maputo, we can see that approximately the expected generation for 1 kilowatt peak, it could be 4.3 kilowatt hour per 1 kilowatt peak. And then we look at the sun peak hours and we have approximately 4.9. So 4.3 over 4.9, that gives us almost 88% of performance ratio, okay? So this map is a very optimistic projection of what we can expect in Mozambique, okay? Remember the references we are saying, for grid connected systems, being very optimistic, I wouldn't recommend more than 85%. Well, this map, depending on the precision we can use, could be telling us, giving us a performance ratio implicitly, which is higher than what I would be recommending. So I am telling you this because of the risk of using sometimes this data. We need to understand what these maps and the published data mean, because sometimes they are giving us results like this map that could be leading us to oversize or undersize our PV system, okay? So always remember what you are learning in this course, the basics, yeah? The key aspects of PV system design, okay? Again, remember, these are maps that average all the values for 1 year in daily values, okay? So this is a lot of averaging here. Again, we have to be careful, okay? All right.
Can I make a question?
Please, yes, Kamal, yes, please.
Yeah, thank you for this realistic approach. But when you are a designer, do you really use these maps or you come and measure things yourself?
Okay, it depends on the time and the level of accuracy you will need, Kemal, because If you want to come up with a relatively, you know, agile estimation, okay, quick estimation, you will be using these maps to be able to know more or less what kind of expected generation you will have in a site, okay? If you have time and you need a lot of accuracy to define your financial plan for the project, imagine you want to build a PV system that you will be selling electricity. You have a power purchase agreement with EDM, for instance, and you need to secure a certain amount of income from your plant, yes, certain amount of generation to be able to, I don't know, pay some loan or something. You need to be really accurate in those calculations. If you have an overestimation of, I don't know, 10% of the output of your plant, and then in reality, you find out that your PV system, your plant, is generating 10, 15% less than what you were expecting. This will mean 10, 15% less of your income through your power purchase agreement. Then you can have a problem with your financials, right? So,
yeah. Thank you.
Sorry?
Thank you. Yeah, very clear. Yeah, I understand that. Yeah. So you start as a rough estimate, and then you start confirming some risks. You know, that you do some sensitivity to see what can go wrong. Yeah. Thanks. Yeah.
Because if you cannot anticipate a financial plan that can be flexible, 20%, 30% more or less, if you cannot make this roundup in a rough estimation, probably that project, you know, you shouldn't invest more time in defining it, let alone installing a pyranometer to record data for 1 year. You understand? You can save yourself all this cost. So it's good to anticipate in this pre-feasibility analysis and use this data, the maps. With the tools the methods I am teaching you, you can do that in a matter of minutes, or a few hours if you want, and then they can help you to proceed to a more detailed feasibility step or not. Okay. So the next.
Can I ask another question?
Yes. See.
Okay. You mentioned before about the oversizing projects versus anticipating future evolution demand. What is the expected foreseens that you have to take in consideration for the few years next? Because yes, I think that you understood the question. What is the foreseen expectation that you may consider in order to accommodate those two things? In one side, to avoid the oversizing projects, and in the other side, to anticipate future evolution demand. I think that you may consider some margin on it in order to estimate what might be the future evolution demand, but not oversizing project.
No, you are very right. This is a very tricky issue. There's no absolute formula for that. Some communities might have a demographic, increased trend. This is something you have to investigate in that particular village. How many, what is the population size? Is it growing 1% annually, 2%, 3%, 5%? This you could investigate. Demographic growth, this is one aspect. The other one, what I mentioned, what are the prospects of, flourishing of appearing of commercial activities, of industrial activities. So you really need to investigate in the area how many shops are about to be open, what kind of activities could be generated there, tourism, I don't know, ecotourism. Is there some kind of telecommunication tower that could go there if there is electricity? So the demand assessment is really something that needs to be done with time and checking with different stakeholders. Apart from that, the PV system is very modular, so you can always add, PV generation panels and more battery banks and more inverters. This is what we call the modularity. So when we design the system, if we can think of modular parts, yes, something that could be upgraded in the future, this is also a good planning recommendation. But there's no way we can say you can always estimate demand baseline and then apply 10%, security margin, 20%. There's no absolute figures for that. Each community will depend, yes? What we know is that in an off-grid community, when there is electricity service starting, very probably that population will grow because there's electricity, you understand? So you should factor that in your analysis. That, I don't know, perhaps the community will grow by 50%, 20%. The best people to investigate that is the people in the same community, in the same village. When you go there and you ask, the community leaders, the people there, they will know, like, when there is electricity in this community, do you expect that many other, citizens, families will move to live here? You need to investigate that, yes? There's no mathematical formula to anticipate that.
I would like to address another simple question. It's about the consumption per day. I saw a few times ago that the reference is about 5 to 10 kilowatts a day per person, not per house. And you mentioned about per house. It is not better we mention.
Mr. Fred, make sure you talk very close to the micro, please. Aproxime-se mais ao microfone, colega Fred.
I saw that we mentioned before the consumption per house, but I saw in the past something referring the consumption per person. In this case, per person in the house, and the estimation that I kept in my mind, it was about 5 to 10 kilowatts hour per day per person. Is it correct?
Again, I mean, this is quite high, okay, per person. It will depend on how many people live in a house, and how families are organized. Because in rural areas, sometimes families can be quite large. You have a lot of children, living together in 2, 3, 4 rooms, So in the end, we normally work with values per family, per household, rather than values per person, because families in the end, they have like buildings, rooms that need to be lit with lights, etc. The reference is normally taken per household and not per person, and you can then revisit these figures, the ones that I gave. Sorry to go back so quickly, but when we look at the tiers, at the demand tiers here, I'm giving you different levels. For instance, this one probably would be the best. You have, for a household, around 8 or 10 kilowatt hour per month. Okay, so if you have 10 people in that household, then you can divide, this reference for the number by the number of people in the household. But in the end, what you will be connecting with a meter is going to be the house. That is your user, that is your customer, like EDM. So you want to have as a reference what the household will be consuming. Not really by person, because you don't really know how many people will be there all the time, okay? So I really advise you to consider the references per household rather than per person. And if you told me 5 to 10 kilowatt hour per day per person, this is very high. I would be surprised that you have that in Mozambique as an average, okay? Per person, perhaps in the cities, yeah, the very large consumers, you could have some percentage of the population, but that could be eventually per household, 5 to 10 kilowatt hour.
Yeah, it's true. It's for urban people, in fact. It's true.
Okay. Yeah, consider it. I suggest, I advise you to use per household, per customer, per meter, if you want. Yeah, because in the end, this is how utilities will deal with the situation. Yeah. Okay, so we were here. All right. Yes. Once we have revisited, yeah, the PV sizing, the calculation of the PV modules, the PV field, we need to look at the structure, yeah, the mounting system. If it is a rooftop system, we need to think about orientation and slope, yeah. How is this PV system going to be installed? If we have a roof of a building that is already built, well, our possibilities might be a little bit, you know, constrained, yeah, restricted to the orientation and the tilt of the roof. We need to consider possibilities of installing, if the roof is not convenient, for instance, as a car park or an open area. In any case, we need to worry about shading, especially in the cities where we have obstacles, other buildings, we have trees, etc. We need to think about which surface of the roof will we find. It's metallic roof, it's tiles, concrete roof, flat roof, etc. And also the kind of building we want to install a PV system. Is it a new building? Is it well built? I mean, the structure is strong, in good conditions. Can we access the roof or not? Sometimes roofs are very difficult to access, etc. For ground mounted, if we put the PV system as structure on the ground, well, this is easier, yeah? But then we need to think about the kind of foundations. How are we going to put that, fix that structure on the ground? We will be on the ground, so very careful with trees, vegetation. Today, we don't have a tree in front of the PV system, PV panels, but after 5 years, we can have something, okay? So we need to plan if something will grow and will cast some shade on the PV panels. If we are in the ground, be careful about potential risk of security, of theft, vandalism, etc. Okay, let's remember some of the things we mentioned. Last week, what could be the different factors that affect the efficiency or the production that we can expect from a PV panel, the tilt, the inclination, yeah, the orientation. These are a couple of websites where you can see, for instance, what would be the, I don't know if this will work now, it's an internet animation. Anyway, you can check it, or I will send you the links, yeah, if this doesn't work. But basically, this website will tell you what is the different levels of power generation depending on the type of orientation and tilt and slope that you can have in a given location. Okay. Let's check. Sorry, this has stopped. Let me fix this quickly. Okay, sorry, just a second. I was trying to open the presentation and it closed. It didn't work. Okay, we are here. Okay, and we are here. Let's check this one. All right. Okay. Okay, I can share now again. Screen. Can you see this now? Yes, it's a website.
Yeah, you can see
Okay.
it.
Okay, this is called the animation, sun motion. Okay, in here you can put the latitude, yeah? We can go to Mozambique, for instance, here, okay? And you can check the time of the year. We can go now, we are here in December, 2nd of December, today, okay? And then we can run the animation. This is how we will be seeing the sun, yeah? In Maputo today, yeah? If we are a person, and depending on the orientation, you will have, can you see? This is the solar path where we will see the sun, yeah? The blue one will be the maximum, okay? In the horizontal, in the horizon, the maximum we can have, and you can change depending on the time of the year. You have more sun or less sun. Okay, the maximum sun you will have in December. So you have these nice tools that can help you to anticipate the kind of position that you will see the sun in a given location. Okay. Okay, I'll stop this now. Continue with the presentation. Coming, just a second. Okay. Okay. You can see the presentation again, right?
Yes, we can see it. Oh.
Excellent. All right. Okay. Okay, so this was the sun motion animation, yeah? Okay, so basically when we have a solar panel, we are worrying about, or we can consider in the design 3 different angles. This one here is the azimuth. This one here is the solar elevation, the alpha. This is changing depending on the seasons, yeah? When it is winter time, for you now it is summer, your sun is quite high. Your sun at noon will get a maximum solar elevation or solar altitude. When you come to June, the month of June, for you, the sun is lower, yes? So the alpha angle will be small at the highest moment of the day. I mean, the noon, the alpha angle will be smaller than in December. Okay, so this is the solar elevation. The beta is the inclination or the tilt of the panels. You know, how high or how flat we will put the panels. And the azimuth will be the deviation towards the north, towards the equator. Yeah, how many angles, whether it is facing north or northwest, northeast. Okay, and this theta angle is the complementary to the alpha for the normal angle with the flat surface, with the ground. Okay, this is important to design to anticipate what would be the necessary distance we need to space our PV panels from one row to the next, okay, to avoid the shading from one panel to the next one, okay? So this is an important parameter we want to calculate, the distance, the interdistance, let's call it B, between panels, okay? This is the formula. I'm going to ask you to calculate some things now, okay? Imagine this is different rows of PV panels. We have a height of the PV panel, the beta angle, yeah, is the tilt. The alpha will be the solar elevation. The sun rays will be hitting, okay, our panels. And then we call this lambda would be the critical shade angle, equaling the solar altitude in the worst day, the worst month, okay? In your case, that would be for the month of June, right? When the sun is lower. Okay, and the formula tells us that this distance B can be calculated by having the H divided by the tangent of the angle alpha, okay? This is the formula. This is trigonometry we can use to calculate the minimum distance between panels. So I'm proposing an exercise for you now. Imagine we want to design a PV system. We want to know what would be the distance between our PV panels, okay? If we have a tilt, inclination, slope of the PV panels 20 degrees, and our PV panels, this size is approximately 1 meter, 0.992 meters. What would be, okay, the minimum distance we need to install to space our different rows of PV modules to avoid substantial shading, okay? You can consider a maximum solar height of 15 degrees. I mean, the minimum irradiation, this value here, this value here, lambda could be the 15 degrees, okay? So what do you think? If our solar modules, PV modules are more or less 1 meter, okay, width here, what would be the distance we need to space them out? Is it A, 2.5 meters, B, 5.6, is it C, 1.27, or B, 4 meters? What do you think? I'm asking about value B, and for that you need H, which is C sinus of beta, and then you need the tangent of angle alpha. Angle alpha, I'm telling you, you can take it as 15 degrees. So, colleagues, what do you think? Which option is the correct for this exercise? Any ideas, any opinions?
Okay, Paul, while they are thinking, can you make sure you change the last D? You repeated B. Should be D of Denmark, not B of Belgium.
Oh, you're right.
You have A, B, C, D.
Yes, that's a mistake. Thank you.
Yeah, yeah.
Yeah, sorry
Eu
about
acho
that.
que todos perceberam a pergunta. Qual é a distância mínima que podemos considerar na colocação dos painéis? Se conhecermos a altura, o comprimento do painel, e conhecemos os ângulos, o ângulo da inclinação do painel, etc, etc. Qual deve ser a distância entre os painéis? Estou a ver o colega Frade, quer falar?
Não, não.
Ah, okay, okay, okay.
So I corrected this. A, B, C, or D. Any ideas?
Could you back to the formula, please? I want to see something.
Okay, this one?
Yes.
Of course, we are taking a minimum, yeah, angle here, because when the sun comes out in the morning, it's right at the horizon, right? So there will always be a little bit of shading, but as the sun starts rising, yeah, from the horizon, then the shade will start disappearing, and then at some point the sun will be, yeah, illuminating, will be on the whole panel. If we bring this panel closer to the previous one, if we make this distance short, the panel in front of this one will be casting a lot of shade, yeah? So we need to space it to a minimum. I'm asking you, what would be the minimum distance? This is the formulas. B, you need to find the H, the tangent for alpha. Alpha B, the minimum solar altitude we want to consider. Any suggestions, any ideas? No, you don't have a feeling for this or a calculation? Anybody? Otherwise, we move on.
I think so. Maybe we move on. Huh?
All right. So the option, the answer would be C. How do we calculate that? We use the formula. B is h divided by the tangent of angle alpha. We said we can take alpha as a minimum of 15 degrees. And for h, sorry, this is a mistake again. Sorry about that. This would be 0.92. Oops, sorry. Sorry about that. This is 0.992. Okay, here we are. Okay, I'm going to share now the screen. Okay, here we are. You can share this one. I can say this one here. Okay. This is where we are. Okay. We take 0.92 sinus of the angle, the slope angle. That will give us the h, and then we divide by the tangent of the minimum solar altitude we are considering, which is 15 degrees. So this gives us a minimum distance of 1.27, okay? For this particular module, and this slope angle we have considered here, okay? So this is a formula you can use to determine the spacing between rows. Then this leads us to a very interesting case, which is that when we put the PV panels in these layouts, we need to space them considerably, as we have calculated. This is an example, but there is another way of, you know, putting the PV panels. Instead of putting them in rows like that, we can put them in this kind of fashion, like little roofs with different slopes. This way, we can integrate between 20 to 30% more panels in the same surface, okay? Because there's less shading between each other. We could lose a little bit of efficiency of productivity, because the panels here are facing north, so very well oriented. And in here, the panels will be facing east and west, so it's not that efficient, but we can put more PV panels to offset, okay? This is, for instance, the example of a PV system. You know where this is? Can anybody identify this city? This is London, okay? And this is one of the most famous museums you have in London. It's the Tate Modern. When you go up to this building here, you can see what happens in the roof of the museum, and you see this kind of PV system. Yeah, this is the River Thames. This is St. Paul's Cathedral in London. You can see how the PV system has been installed precisely in this layout, because there's going to be shading from this same building here, etc. And you can see the PV panels are very close together, so no need for that much spacing compared to the layout of PV panels in this in rows fashion. Okay. So this is another tip I'm giving you when we design PV systems. Okay, what other things we need to worry about? The grid connection. Okay, when we are planning grid connected systems, we need to verify what are the technical conditions, maximum current that could be dispatchable via the existing connection, how is the main service panel existing in the building, current limitations, voltage, the age, the condition, if it has available space for additional series, etc. Otherwise, this main service panel will need to be changed. And obviously, if there are any other utility metering requirements, need to be observed and investigated. Yeah. For the structure design, well, some tips here. Small modules and short strings, short connections that will give us more precision for sizing. That will be very helpful for building integration, photovoltaic panels. If we are planning large PV plants, then we will probably be better off by thinking about larger modules and longer strings, of course. That will enable us to work with higher voltages. This means cheaper cabling, smaller cabling in size, and we need to accommodate the right power condition to dispatch to cope with these large, very high voltages on the DC side. So all of these are design decisions we will need to take. How we connect the modules between each other. Next week we will see an example about how we build the series and how the different type of PV modules and the quality assurance steps we can take to connect which PV modules to which, and how to build equally performing strings, okay, in a PV plant. Again, once we have decided where we're going to put the PV panels, the mounting structure needs to be fixed, okay, on the flat roof. We need to make sure we don't damage the roof, so the waterproofing is kept, thermal insulation. Remember what I told you about the adhesive solutions, yeah? Sometimes, or thin film PV modules are very practical because they can be glued, yeah? No need for bolts, for drilling, etc. Elements on the roof could be a problem. Also the weight load, yeah, especially in weather conditions like what you had last night, strong winds, rains. We need to put ballast loads to fix, yeah, the structure so that it doesn't fly away, right? Okay, same kind of recommendations for ground-mounted structures, the different foundations with concrete, either poured concrete or prefabricated prefab concrete slabs, etc. There's a number of solutions here. This is more about civil works rather than photovoltaic electric design. Then about sizing batteries, remember our exercise that we did in the session. So I explained to you how to size the batteries with the days of autonomy, the depth of discharge, and the selection of the voltage, nominal voltage of the battery. And finally, I want to close today with some words about modeling software. Kemal, related to your question, when we want to do rapid analysis of projects, of course, we can use software, okay? But I want to warn you, okay? Don't use this kind of softwares without having initially done your calculations, your pre-sizing, so you have an idea of the sizing of the main characteristics of the system that you are thinking of. Because this kind of modeling softwares, they will quickly give you some results, but you need to make sure that these results are appropriate, okay? That are accurate, because they will be based on some input data that you will put, and sometimes there are default data in the software. If you are not aware of that, you might be obtaining some results that might not be right. Okay, so be very careful with the software. Probably you need to do some training before using this kind of softwares. So there are many softwares around, okay? Some of them are free to use, but the best ones or the most popular ones we use, okay? PV systems are the three ones I have selected for you. The first one is the Homer, that probably those of you working with mini-grids have already seen or heard about. This is, the website is here, Homer Energy. It's a company, used to be a group working for the National Renewable Energy Laboratory in the United States, Dr. Lilienthal, Peter Lilienthal. It's a very good product, very powerful, specially designed for microgrids. This is the Homer Pro, okay? It's customizable. You can adapt it to the kind of project you want to do. You can consider different generation sources, and you can do very detailed techno-economic analysis with it, okay? You get results like this. You can define the kind of configuration you want to put, AC, DC. You define the load, the demand, the kind of inverter. In this case, this is a Studer. So you have some components in the database. You can choose your batteries, if there has to be a battery or not. In this case, you have a battery here, solar panels, and then a backup. This is a diesel generator, okay? And you can size it, and then you obtain an optimization, okay? And you can perform different sensitivity analysis. But again, this is very good when you have a little bit of a backbone design that you have, you know, thought of, and then you use Homer to perform sensitivity analysis, for instance. You can link Homer Pro with other modules, with biomass generation, hydro, you know, advanced load definition, grid connection, hydrogen, with a MATLAB if you want to perform some kind of simulation on the time series performance of different equipment, etc. So it's really flexible tool, but I recommend to follow some training before using it. And you have to pay on a yearly basis from 500, 1,500. They actually have a lot of packages, so it's better to discuss with them, Homer Pro, the kind of package license you really need for the kind of projects you want to do. Another very popular software that we use is the PV Syst. This is very visual, very educational. It's used for PV system, individual system generation, whether it is grid connected or off grid, and you can perform, as difference to Homer, you can perform more detailed technical analysis of shading, for instance, perhaps not as detailed as Homer in the optimization, okay, and the sensitivity analysis, but still very, very interesting for pre-feasibility studies, okay, and the cost is a bit cheaper. And it can tell you, you know, the different expected generation and production of PV systems. And remember the performance ratio discussion and the different efficiencies, the changes throughout the year, etc. You can model all of that with PV system. And finally, I wanted to discuss, present you the PV Sol. This is, yeah, very complete, very, very powerful software. Again, this is, you have to buy the license and the yearly maintenance. This is a bit more expensive, but again, it has more capabilities, yeah? It has a very detailed component database, very updated, find many, many models of inverters, of PV panels, and you can do very detailed techno-economic analysis. With my colleague, engineer Arnau Alarcón, we will be presenting in January a case for PV rooftop system that has been designed here in Barcelona. This is Barcelona. This is a car park we have. This is an underpass with a bit of an avenue we have in Barcelona. There's a mountain here, and so there's a road that goes underneath the mountain, and there is a car park here. So yeah, Arnau will be presenting how this software was used to design the PV system, almost 80 kilowatt peak PV system, okay, for this car park here, this area here, and how powerful this software can be, okay? Here we can see what the expected generation would be month by month with this PV system that is being designed in Barcelona. So thank you very much. I will leave it here. I think it's now time to close for today. Yeah. Thank you for your attention. Again, you have the materials for this session. We are recording the session, so you can revisit it, yeah, and see it again anytime. And we can have a bit of time for questions, yeah. If there's any question from anybody, any of you colleagues, I'm open for questions, please. Or otherwise, you know, you can write to me with your questions or your comments anytime. This is the email, and some of you are already doing that. So very, very thankful for your questions and your comments. Do we have any questions?
Thank you, Paul. Alguma pergunta, colegas? Alguma pergunta, colegas?
See, I have a question. When you are doing solar home systems, can you hear me?
Yes, I can, yes.
Yeah. You may decide with equipment of for 12 volt or 220. How do you make that decision? Is it available in the market, equipment for 12 volts?
Yes, there is some equipment, but with the lower power, you know, appliances like lights, okay, light bulbs, LED light bulbs. You have some mobile phone chargers. You can have some radios and little appliances. But once you go for engines, any kind of appliance that needs a compressor or or an engine or machinery, you will need AC. Yeah. So this is why solar home systems in DC are normally only installed for very, very small applications, typically only for lighting, okay?
Okay. Okay.
Okay, if there are no more questions, then Dr. Lucas, I think we can close here.
Okay, thank you very much, Paul.